Chapter 2 is titled Functions and Their Graphs. In this chapter, we'll look at a variety of functions, some we know and some will be new. We'll look at their graphs and then we'll look at translating their graphs. In 2.1, we'll start with linear equations in two variables. Hopefully the majority of this lesson should sound like review content. We'll talk about slope of a line, sketching a graph, writing equations, looking at parallel and perpendicular lines, and then of course some application with real-life situations. Starting off with slope of a line, by definition, the slope of a line is simply the number of units a line rises or falls vertically for each unit of horizontal change from left to right. So that's going to be kind of a key in this chapter, anything from left to right. If a line rises from left to right, then it's going to increase like you're walking up a hill. So from left to right, the line goes up. If a line falls, again, from left to right, that means you'd be going downhill. And that's just kind of a way to describe what the graph would look like for different types of slope. Another way to define slope is rise over run. I'm sure you've probably heard that before. And that would be the change in the y values divided by the change in the x values. So as long as you have two coordinates, we'll identify them as x sub 1 and y sub 1 for 1 point. And then the other pointer coordinate would be x sub 2, y sub 2. To find the slope given any 2 points in a line, we take the two y coordinates and we subtract them. So we find the difference in the y values, that's the change in the rise. Divided by the difference in the x values, that's your horizontal change or the run. And then always simplify, and that's your slope. So let's try a couple down below. It says find the slope of the slope of the line passing through each pair of points. In that first system, or that first set of ordered pairs, we'll identify them as x1, y1 and x2, y2. And then you literally just plug it into your slope formula. So we'll say slope equals y2 minus y1, which would be 1 minus 0, divided by x2 minus x1, so we have a double negative. 1 minus 0 is 1. 3 minus negative 2 becomes 3 plus 2, which is 5. The slope is 1/5. From left to right, the line rises because the slope is positive. Let's try another one. Negative 1, 2, and 2, 2. Again, identify your coordinates, x1, y1, x2, y2. And then just follow the definition for the formula. y2 minus y1 becomes 2 minus 2. x2 minus x1, 2 minus negative 1 again, so we have that double negative. In the numerator, we have 2 minus 2, which is 0. In the denominator, we have that double negative, which turns into 3. Well, 0 divided by anything is 0. And if you have a slope of 0, that means it doesn't rise or fall. This would be a horizontal line. So from left to right, it just goes straight across. It does not rise or fall. The next one, 0, 4, and 1, negative 1. If we take a look at this one, 0, 4, and 1, negative 1, x1 and y1, x2 and y2. Now if we do y2 minus y1, that's negative 1 minus 4, over x2 minus x1, 1 minus 0, we get negative 5 over 1, which simplifies to negative 5. So from left to right, this line has a pretty steep slope and it would fall on the graph. One more example, 3, 4, and 3, 1. Identify your coordinates, x1, y1, and x2, y2. One last time with our slope definition. If we do y2 minus y1, we have 1 minus 4. But x2 minus x1 is 3 minus 3. And when we reduce this fraction or simplify, we get negative 3 over 0. And this should be kind of a caution right here. If you have 0 in the denominator, that means the slope isn't 0, it's actually undefined. And if you have an undefined slope, that means from left to right, you're not actually changing your x values at all. It's just going up and down. So this is an example of a vertical line. When graphing linear equations in two variables, we want to try to be as efficient as possible. You'll typically be given a linear function in one of two forms, what's called slope-intercept form, and that would be the most common for us, but we've also seen equations in what's called general form for a linear equation with two variables. The slope-intercept form is the most common form, and looking at this model, we know that the slope is the m value. It's always the coefficient right in front of x, and that'll tell you if it rises or falls, if it's steep or not too steep, those kinds of things. The y-intercept is always kind of a good starting point on your graph, and that's what's written after that mx value. Now, general form is unique because both variables for x and y are on the same side instead of getting y by itself. When this is the case, your slope formula isn't quite as easy, but I want a different color, so let's get rid of that one. I want it to match the blue. When you want to find slope in this form, we now look at a couple of the coefficients and we compare them. To find slope, it's just negative a divided by b. And a is the coefficient in front of x, and b is the coefficient in front of y. To get the y-intercept, you would take plane c divided by b, and the c is always a constant on the right-hand side. And these would be the answers these would be the answers you would get if you got y by itself. So the last thing we're going to do is just sketch a couple of linear functions, and that'll be good for our video today. Taking a look at our first equation, y equals 2x plus 1. Because it's already in slope-intercept form, we know the slope is the number that's in front of x, and that's just 2. And I'll write it as 2 over 1 in fraction form, rise over run. The y-intercept, which will be a good start point for us, is always what's written after, and that is 0, 1. So to graph this line, start at 0, 1 and plot that point on the y-axis. Then use your slope formula, count up 2, 1 to the right, and up 2, 1 to the right. Go as far as you can in that direction. Do the same thing in the opposite direction. Go down 2, 1 to the left, so it follows the pattern of that slope. Connect your dots all the way through your graph from edge to edge, and then use arrows to designate that you have a linear function. The next example, y equals 2, is missing something. Technically, it's missing the x value, so that would mean y equals 0x plus 2. And that's significant because that means your slope is 0. So from left to right, there's no rise or fall. It's just a horizontal line. And the y-intercept, since it says y equals 2, that's your y-intercept, 0, 2. If I plot that point, that's right at 2 on the y-axis, but this is a horizontal line, so I really don't even need to draw any other points on my graph. Horizontal, there we go, missed the T there. Hello, Diesel. We have Diesel the cat, everybody, helping us out today. Thank you for getting in my way. Okay, carrying on. Now, if it's a horizontal line, like I said, we'll just draw a line straight across, all the way edge to edge, with arrows at the ends. Last but not least, we just have one more, x plus y equals 4. Now, this would be easy enough to get y by itself just by subtracting x to the other side. But I'm going to apply the rules for general form just to show you how it works. Since it's in that general form, to get our slope, we're going to follow that model, negative a over b. And a and b are both technically 1 since there aren't coefficients listed. So it would be negative 1 over 1, which reduces to negative 1. The y-intercept is that other fraction definition, c over b. And in this case, it works out pretty nice for us. It's 4 over 1, which is 4. And just like the other two lines, this is the information we need. Start at the y-intercept of 0, 4. I guess I should have written that as an ordered pair. 0, 4, all the way up here. And the slope is negative 1, which means I'm going to count down 1 and 1 to the right, all the way to the edge of my graph. And then I'll do the same thing just right up there at the top in the other direction. Connect all your dots, kind of a nice thing there, with arrows at the end. We'll finish the rest of the notes tomorrow in class.